So we've been asked to take a look at this problem. I've chosen a sample here. Here's our function. It's a rational function, 3x squared plus 6x minus 45, and that's all over another quadratic, x squared plus 3x minus 10. And for this, we want to take a look at the domain, the intercepts, the restrictions. Now, obviously, the domain and the restrictions are going to tie into each other. So it's not as if you have to blindly do this just in this order. You should feel free to jump around a bit if you want to. And then we're also going to look at the interval table. And then once we've got that, we're going to sketch a graph of this, making use of these features that we've come up with. When you're doing questions like this, you always want to start off with some sort of factoring. And in this case, whenever we do factoring, you want to start with common factoring. So I'm going to start with that right away. You might notice that our numerator has actually a numerical common factor of 3. And so I can actually rewrite that as x squared plus 2x minus 15. And the denominator is going to just stay the same, x squared plus 3x minus 10. I could have gone ahead and factored that one there, but I'll do that in the next step. So in the next step, I'm going to leave that 3 out. Two numbers that multiply to negative 15 and add to positive 2. That's going to give me x plus 5 and x minus 3. And in the denominator, two numbers that multiply to negative 10 and add to positive 3. That's going to be an x plus 5 and an x minus 2. And you can see why I chose this problem in particular, what I was hoping to have happen. We've got a common factor of x plus 5 in the numerator, x plus 5 in the denominator. Those are going to divide out, and that's going to give me the result of 3 times x minus 3 all over x minus 2. And now in this case, because we have divided out this factor of x plus 5, because it was common, in moving from this step to this step, I have actually removed some information about the function, and that information had to do with this factor x plus 5, and in particular it had to do with dividing by this factor. Well, we know we're not allowed to divide by 0, so now that we've removed this factor out, we actually should indicate that, oh, by the way, to anybody who's reading this, by the way, x is not allowed to be negative 5, because I've taken out that piece of information, and so here is this is essentially preserving that information. So this original function is going to look exactly the same. The graph of this original function is going to look exactly the same as this simplified function, but we have to beware of the fact that we have at x minus 5, we are going to have actually a whole at x minus 5. Now, if you wanted to, you could go ahead and substitute that in and find out, well, where exactly is the whole? And so since we're talking about that, why don't we go ahead and do that right now? So we've got our whole here at x minus 5. And so I'm going to just say, well, what is f of negative 5? You might say, well, hold on, if I put f of negative 5 into my original function, I'm going to end up with a 0 over 0, and this is true. But what we're trying to figure out is, well, what are the coordinates where that takes place? What is this point that we're trying to avoid? And we can actually substitute negative 5 in for x in the simplified function to get an answer to that question. And so we're going to end up with 3 times negative 5 minus 3 all divided by negative 5 minus 2, and that is equal to, so we get 3, negative 5 minus 3 is negative 8, negative 5 minus 2 is negative 7, and so we end up with our whole at negative 24 over negative 7, or positive 24 over 7. So that means our whole location is at the coordinates negative 5, 24 over 7. So we've got that. So now that we've done this, this might be a good time for us to, we've kind of gone a little bit off in our own direction, which I told you was fine, but we really might want to actually say, well, you know what, I have an answer to part A right now, which is the domain. So the domain of the function f is equal to the set of all x member of the reals such that, and in this case we can see I have an obvious restriction here that's left behind, x is not equal to 2, and I have the restriction that I divided out, which was for the whole, x is not equal to -5. So there's the first part. There's my restriction, there's my domain. Alright, so let's go ahead and continue with this. I'm just going to move along here. I'm going to keep my simplified function visible. Okay, let's take a look actually now at the intercepts. So the easiest intercept is to find the y-intercept, and to do that I'm going to set my x value equal to 0. And essentially that means I'm going to solve, in this case I've got a function f of x, so I'm going to find out what is f of 0. And I'm going to use my simplified function to find this. So that's going to be 3 bracket 0 minus 3 all divided by 0 minus 2. And that works out to be, so 0 minus 3 is -3, 3 times -3 is -9, 0 minus 2 is simply -2, and so we end up with positive 9 over 2 or positive 4.5. It's up to you how you want to express that. This is a non-repeating decimal, so it's fine to represent this as a decimal. What about the x-intercepts? So I'll maybe do that over here to the side. So for the x-intercept, I set y equal to 0. Now this is going to be a little bit more involved, and actually when I say set y equal to 0, in this case because I've got function notation, that's the same thing as saying f of x is equal to 0. Let's represent that differently. So instead of saying set y equal to 0, I'm going to say set f of x equal to 0. And again, I'm going to go ahead and use my simplified notation. And there's a reason for that. Let me go ahead and I'm going to do this first. So we've got our f of x is equal to, if you take a look up here, f of x is equal to 3x minus 3 over x minus 2. And that means I need to solve now for 0 equals 3 times x minus 3 over x minus 2. Now, in order to solve this, to simplify it, I've got a few options, but the easiest one is simply to multiply both sides by x minus 2, and of course multiplying 0 by x minus 2 gives me just a 0 again, and multiplying the right side by x minus 2 is going to cause these factors to divide out, leaving me with 3 times x minus 3. And again, it might be worthwhile at this point to make a note of the restriction that we've got here. Now we already have this restriction in our domain, which is that x is not equal to 2. Now the reason why I'm including this restriction here is just to remind me that when I solve this equation, the answer x equals 2 and the answer x equals -5, those can't be a solution that I'm allowed to use. In this case, simple enough, 3 is obviously not 0, which means that x minus 3 equals 0, or x is equal to 3. No, that didn't work very nicely. Hold on a second here. Shift up a bit. And we end up with x equals 3. Now remember, these are intercepts. And so that means I have a y-intercept. Just to summarize, my y-intercept is a single point. And so this is where x equals 0. So this is going to be the point 0, 4.5. And my x-intercept is also this point where x is equal to 3, and y is equal to 0. And I just want to make a comment here about that I used f of x equal to 3 times x minus 3 over x minus 2. 3x minus 3 over x minus 2 for the x-intercept. And the reason why that's an okay thing to do so why does that work? Why is that okay? The reason why that's okay is because if the whole had been one of our x-intercepts, it would have shown up already. So this works because if the whole was an x-intercept, we would have discovered it already. Okay, sorry for taking the time to write all of that out. Okay, now it turns out the whole was not one of the x-intercepts. The whole did not have it didn't have a y value of 0. It had a y value of 24 over 7. Okay, so now we've got our intercepts, we've got our domain, we have our simplified function. We need to identify, well, what do those restrictions actually stand for? Well, we've already talked about the whole. What's the other restriction we have here? We have a restriction that x is not equal to 2. I guess I should have said, instead of just saying this as restrictions, I think I originally said in my original question, I think I said asymptotes. And that might be more useful because we don't just want so asymptotes and wholes. And while that has something to do with the domain, we also need to consider horizontal asymptotes. So let's look at that now. Is that going to fit on this page? Yeah, I think we can fit that in. So let's take a look at part C, which would be our asymptotes. Now, first of all, we have a vertical asymptote. We already have our whole. Maybe I'll summarize that here. We have a whole, and the coordinates of that whole are -5, and the y value was 24 over 7. 24 over 7. We have a vertical asymptote. Our vertical asymptote occurs at x equals 2. And we take a look at if you look at the original expression all the way to the top, the original expression was a quadratic over another quadratic. That's order 2. 3x squared is order 2 over 1x squared, also order 2. So that tells us it's going to be a horizontal asymptote because the orders are the same, order 2 over order 2. And because they're the same, the asymptote itself is simply going to be the ratio of the leading coefficient of the numerator over the ratio of the leading coefficient of the denominator, which is equal to 1. And so 3 over 1, so the horizontal asymptote is y equals 3 over 1, which of course is simply 3. So there we have our whole, our vertical asymptote, our horizontal asymptote. So now I'm going to move on to a new page, and from that we need to, what else do we need to do? We need to create our interval table. Now our interval table is going to be based on, just as it was when we did the unit on polynomials, it's based on where we cross 0, so that's the actual zeros, or any asymptotes, any discontinuities along the x-axis. So again, this idea of the whole If we had had another intercept at the hole, if the hole had turned out to be another x-intercept, we would have had to put this on our interval table. But as it turns out, we don't have anything there. So the items that will go on the interval table are going to be the location of the vertical asymptote and the, where did we find it, and the 0. So those are the two items that are going to go onto the interval table. So let's switch to the next page. And we're going to do part D now, which is our interval table. And so for that, I'm going to use my vertical asymptotes or my zeros. So what were those vertical asymptotes? Just to remind you, we had a vertical asymptote at x equals, just going to switch back here, quick look. Vertical asymptote at x equals 2 and a 0 at x equals 3. And 0 at x equals 3. So when I go ahead and draw my table, then I'm going to be using, now what were the factors? Maybe it would be if I grabbed a hold of the simplified function. So it's 3 times x minus 3 over x minus 2. So f of x is equal to 3 times x minus 3 over x minus 2. And so for my interval table, I'm going to use the value 3, the factor x minus 3, and the factor x minus 2. And for those, my first interval is going to be based on the value 2, and that one is a vertical asymptote. And my next interval is going to be based on the value 3, and that's a 0. And that means that these intervals, this one's going to be negative infinity to 2, this one's going to be 2 to 3, and this one's going to be 3 to infinity. And break these up into our table. And then our results. Okay, so when we put in, obviously 3 is always a positive number. So those are all positives. When we put in a large negative number, this is going to be negative, a large negative number here, and so the result is positive. When we put in a number between 2 and 3, so 2.5, that's going to be negative, 2.5, that's going to be positive, ends up being negative overall, and a large positive number is going to cause these to be positive, which gives me an overall positive. Technically, you don't really need this, but it does help. You can do it other ways. We've talked about the idea of using tables of values, etc. So now let's go ahead and try to graph this thing. See what that's going to look like. So I think I'll grab some straight lines instead, if I can find the straight line tool for this one. No, I don't think it's that. Oh, yeah, that's the one I want right there. Well, that didn't work out so well. Let's try that again. Get rid of those. Let's get that x-axis a little bit better. So we'll actually try to put it on a line. And again, that's not what we wanted. There we go. That's a little bit better. And we'll use 1, 2, 3, 4, 5, 6, marking 5, and -1, -2, -3, 4, 5, 6. And I think I'll use a smaller scale here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, -5. And where do we have something significant taking place? We have a 0 at x equals 3, and we have a vertical asymptote at x equals 2. So at x equals 3, we have a 0, which I can mark. At x equals 2, actually, let's change the color for that. At x equals 3, and then at x equal 2, I have a vertical asymptote. And what else do I have? I know where I have positives, I know where I have negatives. I also have to take into account my intercepts. I have an x-intercept at 0 and 4.5, and I have a hole at negative 5, 24 over 7, which is about 3 point, is that 3.5? Yes, not quite, no, a little bit less than 3.5. So negative 5 and a little bit less than 3.5. So over here at negative 5 and about just short of 3.5, I've got my, sorry, that's my hole. And I said that I had an x-intercept, sorry, I had a y-intercept at so that one's at negative 5, and my y-intercept is at 4.5. So y-intercept at 4.5, a little bit higher here. And then if we take a look at the other information we've been given on our interval table, from negative infinity to 2, it's always positive. Oh, there's one other thing I didn't put in here, which was the horizontal asymptote, which was at 3. So there we go, it's at 3. And now when I go ahead and I graph this, well, you can see there's really only one thing you can have for this left side. From this hole, it's already so close to the asymptote, it's just going to continue going along there. This is actually going to be very difficult for me to draw smoothly, so please forgive me for a less than perfect drawing of this. And then it's going to go towards the vertical asymptote. And then we take a look between 2 and 3, our result is supposed to be negative. So between 2 and 3, our result is supposed to be negative. Well, between 2 and 3 is between the vertical asymptote and this hole. So that's saying that from here downwards, as it approaches this asymptote, it's negative. And then it's positive from 3 to infinity. And there we go. So, and you can see in particular, I just want to highlight for you that the value we found for that hole, the coordinates of that point, negative 5, 24 over 7, actually makes sense. You can see this is just above the value 3. 24 over 7 is just above 3. So all of our values, intercepts, the location of the asymptotes, etc., all work together to allow us to come up with the overall graph. I hope that was helpful, and of course feel free to review this at your leisure, and I hope it helps make sense out of this particular type of problem.